Are you guys able to see my screen? With this thing? Okay, cool. Okay, none of the videos is on. Okay, Bihan has made the entry. Okay, cool. Okay, let's discuss the homework from last time. Okay, so the first couple of questions should be fairly, a few questions are easy only, some questions are hard. List the factors of 480 in ordered pairs. Avinash, how many did you find in total?
24.
24. So basically question 1 and 2 is just to compare and contrast how long it is to list, but how easy it is to count. So counting means you just have to give how many. You don't have to list them. Listing means you have to list. So if you have to list, so you say 1 into 480, 2 into 240, 3 into 160, like that, right? We keep going. The last one will be 20 into 24 when approximately 20 and 24 are next to each other, right? That's when we stop. So that takes a long time. Counting is much faster. So how do we do the counting? If you just want to count, we'll use the power, right? So 480 is, we'll use the prime factorization of 480. So 20 into 24, always try to split it as big numbers so that it's easy. So 4 and 5, this is 4 and 6. So this 4 is 2 power 2, this 4 is 2 power 2, and then there is 2 in the 6. So that's 2 power 5. There's 1 3, which is in 6, and then 1 5. So it's 2 power 5 into 3 power 1 into 5 power 1. And as we know, the number of factors will therefore be 6 into 2 into 2, which is 24 factors.
Sir, but if you're looking at ordered pairs, won't it be 12?
Yeah,
Because...
yeah, correct. Yes, correct. 12,
it'll be 12.
12 ordered pairs. Yeah, 12 ordered pairs. Correct. I'm just asking you to list the 12 ordered pairs. Correct. Answer would be 12 ordered pairs, therefore 24 factors. Okay. Question 2, how many factors will 1440 have? Just a slight extension to the earlier one, right? So Ananya, how many did you find?
Oh, is it 24?
24 for this as well. 1440 should be more, right? Because 24 is 480 times 3. So 480 itself was 2 power 5 into 3 power 1 into 5 power 1. Therefore,
I got 36.
36. Yeah. So this will be, number of factors would be 6 into 3 into 2. Yeah.
Yeah,
So
that's
that's
36.
36 factors.
So, but again, listing it as ordered pairs, it'll count to 18.
Yeah, 18. Count the number of
But
factors.
they've
in ordered
asked the
pairs.
number of factors.
Number of factors. Yeah. So this is more like, it's not an AMC question, right? It's more like a warm-up type of question, just to understand the concepts. Yeah. Just counting the number of factors would be 36, but as you said, number of ordered pairs would be 18.
So what are ordered pairs?
Or ordered pairs is pairs where the ordering matters. So for example, if you're labeling points on the graph paper, XY plane, so 3, 7 is not the same as 7, 3, right? If it's just a pair of numbers, doesn't matter. 3 and 7, the ordering does not matter. But if you look at 2 points, 3, 7 versus 7, 3 on the number line, there are different points on the plane. There are different points. Therefore, we call their ordered pairs, right? The ordering matters essentially, ordered pairs. As opposed to just saying pairs, the ordering does not matter. It's like choosing versus arranging. Okay. Question 3, find the HCF and LCM of okay, 720 and 3234. You can just tell me in terms of powers of prime numbers. That's fine. Apurva, what did you get on this one?
So actually, like I misunderstood the question, so I just wrote it as like HCF and LCM is equal to product of the two numbers. I didn't get it into the prime factors.
So I did the prime factorization for 720.
Yeah.
And I got 2 raised to 4,
Mm-hmm.
3 raised to 2, and 5 raised to 1.
Okay, let's check 16 into 9, 144 into 5. Yeah, correct. Okay, and 3234 would be?
Sorry?
3234 ka prime factorization.
3234. Oh, 1 second. I got 2 raised to 1.
2 raised to 1.
3 raised to 1.
3 raised to 1.
7 square and 11 raised to 1.
Okay, so 6, 66 and 49. Yeah, seems more like it. Okay, cool. And therefore the HCF would be just 6, I guess, right?
2 into 3. Yeah, 6.
2 into 3, which is 6. And the LCM will be the 2 power 4 into 3 power 2 into 5 power 1 into 7 power 2 into 11 power 1. Big number, right?
Yeah.
Okay. And
Yes.
yes, as Apurva was saying, the HCF into LCM will be the product of A times B. But why is this, Apurva or anyone? Why is the product of HCF and LCM the product of the two numbers? Can someone formally prove this? I mean, formally means you don't need a very elaborate formal proof, but some proof. Yeah. Yeah, Apurva, go ahead. I'm asking you only.
So I'm not sure, but like the way you calculate the LCM from the prime factorization is basically like, so for example, if you take 720 and 3234, I'm not sure, but wouldn't it be 2 raised to 5 into 3 raised to 2 or 3 raised to 3? But like it's something to do with the prime factorization. I'm not sure how you
It is
do it.
completely to do with the prime factorization. Not something, but completely to do with that only. But yes, using prime factorization. Anyone wants to take a shot? Ananya, you want to go?
So in HCF we only take what's common, and in LCM we take the maximum value.
Correct.
So when we multiply the two numbers, we get the maximum value plus the like value that was common.
Correct. But question is like, why do we get that? Can you elaborate a little bit? Yeah, you're on the right track only, but
So when we sorry.
no, you are on the right track. Maybe do you want to annotate or write something?
No, sir.
Okay, Rohan, you want to give it a shot? Or anyone?
So is it because, wait, no, that's the same thing as what she said now.
Yeah. So yeah,
So
yeah. Go ahead, Rohan.
when you take the HCF, and you look at the LCM will be the highest power, and the HCF will be the lowest. And like when you multiply those two, so suppose on one side you have 2 raised to 4, and on the other you have 2 raised to 2. The HCF will be 2 raised to 2, but the LCM will be 2 raised to 4. And then when you multiply those two together, you get 2 raised to 6, which is the actual multiplicative answer.
Exactly. Very well said, Rohan. And that's exactly what Ananya also wanted to convey, but she didn't finish it up full. Yeah. So basically just to say, so this is, let's say 2 power 3 times 3 power q times 5 power r and so on. Okay. And let's say B is 2 power, let's take some other number, x, 3 power y, 5 power z and so on, right? And when you say HCF, it's the minimum. So between x, whichever is the minimum. Okay, for now, let's assume all of these numbers are not equal, right? P is not equal to x, q is not equal to y, r is not equal to z, something like that, right? So let's say the minimum is P, then the maximum will be x among the two. It will appear here. Let's say the minimum here is y, between y and q, this is q, and the maximum is q, right? And similarly, for every power, the minimum or a maximum has to occur in one of them. And of course, if they are same, let's say this is 7 power d here and same 7 power d here also. Doesn't matter. You're going to put it in the HCF and you're going to put the same quantity in the LCM also, right? And yes, and therefore, effectively, the product of these two is same as the product of these two. Okay, it only works with two numbers. Another way to look at the same thing is, okay, let's say A and B, right? So HCF is H. So this is H times some number M. Okay, and this is HCF times some number N. Okay, HCF is the highest common factor, right? Now, the premise is we are saying LCM is H times M times N. If we say that, we will come to why that is the case. But if this is true, So if this is our premise, if n equal to h into m into n, then we are done. Because if so, then h times L will become h times m times n, which is exactly what we want, right? Because h times m times h times n is your A times B. Okay, but why is LCM h times m times n? H is common, right? So we need h, and m and n do not have anything in common, right? Therefore, to find LCM of A and B, I bare minimum need h, and m and n do not have anything in common. Why do m and n do not have anything in common, Kunsh? What if m and n had something common? For example, let's say HCF is 36 and m is 20. Let's say this is, and the HCF is 36 and n is, I don't know, some other number, right? 12, let's say, right?
Yeah.
Is this sort of situation not possible? Or maybe I'll just say 22, something like this. So this is m and this is n.
Because there's parts of M and M can go into H, so it's not possible. It doesn't make any sense.
Exactly. Yes. If this were the case, then 36 will no longer be the HCF. 72 would be the HCF. So you'll absorb everything as much as possible, squeeze out everything, and only the balance is your HCF. Therefore, these two by definition cannot have anything in common. And therefore, the product of H times M times N is your L. And this works, the H times L is A times B. That works only when there are two numbers. If there are three numbers, A, B, and C, there's no such thing, right? I cannot say the product of H and L is the product of A, B, C. That's not possible. Only with two numbers it works, because the maximum and minimum have to occur in one or the other. Okay, all good, right? Vihan and Kunal, your videos are off. Please turn on, please. Okay, that was question 3. Okay, question 4 was an interesting one. How many ordered pairs M and N such that LCM is 120? Okay. Anahat, did you get an answer on this one?
Yeah, I got 29.
29.
Yeah.
Okay. Tell me the logic, please.
I just found how many factors of 120 there are. And then
How- Okay. How many factors? So 120 would be what in prime factorization? 12 times 10. This is 4 times 3. This is 2 times 5. So it's 2 times 3, 3 and 5, correct?
yeah. And then
Okay.
that gives you 4 times 2 times 2. Yeah. 16
Which is
factors.
16 factors. Okay.
And so 120 is one of the factors, and then 120 comma each of the other 15 factors will be one pair each. So that's 15 pairs.
Okay.
And then after that, I just the other 14 I just kind of had calculated. It's gonna be out of the factors, so I just mix and match the factors. And
Okay. Okay. So first of all, one thing, it says how many ordered pairs, right? So if you say 120, 2 is a pair, then 2, 120 needs to be counted separately. Okay. So that itself will be double. So 15 into, so there are 15, 15 factors other than 120. So 120 can be clubbed with, like you said, with each of them. And then you have to double, right? So there are 30. And then there's 120, 120 itself, which is one more, which is 31. But then that's only with 120 being one of the numbers. With other numbers, also you get multiple answers, right? For example, let's say 60, 40. That'll be in one of your 19 that you counted, hopefully, right? 19 or whatever you counted. But it becomes too tedious, right? Let's say this number is 120. Even with a small number like 120, it's difficult. And you can never be sure that you have exhausted everything. In fact, even assuming this times 2, even if you keep that aside, it should be more than 19. As in you found only 4 more, you're saying.
I got 29, not 20.
Oh,
So
29. You got 14.
Yeah, so
more.
I guess I didn't multiply by 2, so I guess it should be then.
Okay. So you got 15 plus another 14 more.
Yeah,
So
15,
yes, okay. But again, you cannot be confident that you have captured everything, right? Do you agree, Anahat? Okay.
Yes.
So anything more like solid, foolproof you can do other than, yeah. Another problem is you literally have to list out everything. Right? Again, listing versus counting. The question is only how many. We just have to count. We don't have to necessarily list. So it becomes a waste of time to list, especially as we get to bigger numbers. Yeah. Anyone else with any other answer other
I
than
got 63.
63? Okay. What was your logic?
So like for each of the numbers m and n, I took 2 to the power x, 3 to the power y, and 5 to the power z. And for n, I took 2 to the power a, 3 to the power b, 5 to the power c. So x and a have to be less than or equal to 3. Y and b have to be 1 or 0, and Z and C also have to be 1 or 0. So in that, I calculated all the possibilities and then I multiplied it.
But how do you calculate? So can we go through? So x and y can be either x and y, x and a, sorry. So this is your m, and this is your n. Okay. So you're saying x and a can be anything from 0, 1, 2, and 3.
Yes.
Likewise, your y and b can be anything from 0 or 1. And similarly, your z and c can be anything 0 or 1. Okay. So far, so good. Now, how do you count, please?
So like 0, 3,
Mhm.
1, 3.
So you put 0 here, 3 here, 1 here, 3 here.
Yes, sir.
Okay. 2 here, 3 here, like this.
Yeah.
And then
3, 3, 3, 0, 3, 1, 3, 2, 3.
okay. So how many did you find?
So 7.
7. Okay. Okay.
And then so I took for the next two I found 3. So 7 into 3 into 3.
Excellent. Yes, exactly. Okay, but we can do it slightly shorter, but exactly for this small number, this is perfect, right? So understand what she's doing, right? She wants to have a 2 power 3 in at least one of m or n, right? So she wants between x and a, she wants a 3 for sure. So it can be 0, 3, 1, 3, 2, 3, 3, 3, or 3, 0, 3, 1, 3, 2, 3, 3. Of course, 3, 3 is getting repeated, which is why she's counting 7 of them. Similarly, between y and b, she wants at least one of them to be 1. Only then you'll get 3 power 1 in the LCM. So either 0, 1 or 1, 0 or 1, 1. So 3 options as far as powers of 3 are concerned. So this is powers of, okay, so the first block is powers of 2. This is 2 power. This is 3 power. And then the last one is, a last block is, let's say, 5 power. So for 5 power also, you have 0, 1, 1, 0 or 1, 1. So she has a total of 3 here. So now she can mix and match anything, and she can say 7 into 3 into 3, right? An example would be, let's say she picks this, this, and this. So the meaning for that is your m is going to be 2 power 2 into 3 power 1 into 5 power 0. So m is 2 power 2, right, into 3 power 1 into 5 power 0. And n is, she's picking 2 power 3 into 3 power 1 into 5 power 1. So that way, the LCM is 2 power 3 into 3 power 1 into 5 power 1, exactly what we wanted. Okay, does it make sense, guys? Okay, now we can do it a little bit more. We can do slightly one more step better than this. How did she arrive at this 7? She arrived at this 7. Oh, okay. In fact, I'll make it this way. So let's say there are 2 numbers. So not 2 numbers. Let's say instead of 120, I have a number which is instead of 120. So not 120, but instead of 120, 2 power a times 3 power b times 5 power c. Okay, where a, b, c in this problem were something else, 3, 1, and 1. In general, in terms of a, b, and c, can you come up with some formula for the number of ordered pairs m and n? Question is clear? So in other words, now that she has established a process, you would have seen, right, how she arrives at 7, 3, and 3. Can we arrive at those same numbers in a more formulaic approach rather than listing approach? Can you guys give it a shot? All of you clear what I'm talking about here, right? Yeah.
So can you repeat the question?
Okay. Now, do you understand how we got 63 for this one, right?
Yeah.
Okay. Now, more generally, for a number n, in terms of A, B, and C, what will the 63 be? Instead of 63, it's something else. What
So
is
is
that?
this formula that you're using to just 2n plus 1 over to get these 733.
Good. But why is it 2n plus 1? Good.
So
So
that's
good.
because you can have basically it'll actually be I forgot what to say. Be 2n plus 2 normally, and then you do -1 because there is one common in this one. That's there.
Correct. Brilliant. So it's 2A plus 1 choices here, 2B plus 1 choices here, 2C plus 1 choices here. But why is that? Your pattern recognition was spot on. I mean, can you elaborate why 2A plus 1?
So that I found, see, because there were 0, 1, 2, 3, and then it goes back down to 0, 1, 2, 3, and then there were 3 at the top. So that's why there are 4 in each way. So 2 into n plus 1. And then because there's one common, you have to cancel that. So 2 into n plus 2 minus 1, 2n plus.
Perfect. Perfect. So what he's saying is, so the power of 2 is A. So which means the number of, sorry, I get confused between this A and this A. Okay, let's stick with this, right? So we can go all the way from A0, A1, A2, all the way till AA. So from 0 to A, it's A plus 1 numbers. Like that from 0A, 1A, 2A, all the way till AA. So that's also A plus 1 numbers. The only commonality would be the AA, which you have to subtract to avoid double counting. So it's 2A plus 1. So 2 times A plus 1 minus 1 for the double counting, right? So it's just 2A plus 1. And likewise for B, likewise for C. So once you've listed out all of them, it's just the product of all of them. Does it make sense? Another way to think of this, the same 2A plus 1 is, how did you get this 7? This 7 was, X could have been, so I'll just call it P, Q, and R so that I don't want to confuse with this, right? I'll just call it P, Q, and R. Okay. X could have been 0, 1, 2, 3. P could also have been 0, 1, 2, 3. So there are 4 into 4 possibilities, 16 possibilities. But among them, you don't want the case where X was also a number from 0, 1, 2, and P was also a number 0, 1, 2, because that means the maximum was not 3. To ensure maximum was 3, right? You subtract off those cases where the maximum is not 3, right? The highest power is not 3, which means it's 0, 1, or 2, or 0, 1, or 2. So it's 4 times 4 minus 3 times 3, which is the same thing, right? In fact, what is this 4? The 4 is your A plus 1. So it's A plus 1 square minus A square, which is your 2A plus 1, right? A square plus 2A plus 1 minus A square, which is the same 2A plus 1 that Avinash observed by pattern recognition. So all of this ties together. Does it make sense? Okay. Sana, Anahat, Kunal, video on, please. Kunal, your video has been off all day. I haven't seen you at all. Unless your mom messaged me. Okay. All right. Okay. So that was this. Okay. Just for practice, can we just try one more number of the same kind? So let's say how many ordered pairs where the LCM would be 1000. Can we just try this so that we are all on the same page? Instead of 120, it's 1000. Can we tell? Ordered pairs MN, and it takes care of ordering also, Abhyana. You don't have to worry about multiplying by 2 and all that, right? Ordered pairs, LCM of M and N should be equal to 1000.
So I'll just be back in like 2 minutes.
Yeah, sure.
So I got 49.
49. Okay. Yeah. So this is 10 cubed, right? And 10 is 2 into 5. So this is 2 cubed into 5 cubed. And as we just saw, the odd pattern was 2A plus 1 times 2B plus 1. So 7 into 7, 49 indeed. Yeah, makes sense. Well done. Okay. I'm just thinking another question.
So what exactly are ordered pairs?
Ordered pairs means pairs with where ordering matters, as I was telling earlier in the class also. right? So if you say 3, 5, that pair is different from 5, 3. You're saying ordering matters. These two are supposed to be counted as separate entities. That's all ordered pairs. Okay, I'll skip question 5. Use prime factorization to determine HCF and LCM. It's just more for practice I'd given. Question 6. Okay, question 6. You need to check if 7907 is prime. You want to minimize the number of checks. Okay, what's the minimum number of checks? Right, it's a little bit open-ended question. It's not like AMC10 type of question, more like to understand the concept well. Right? Yeah, Kunsh, how typically to check if 7907 is prime, you'll check divisibility by what all numbers?
I go 2, 3, 5, 7, 11, 13.
And so on till?
Until I go till usually 23.
Why 23?
I don't know, it just feels like a good number. So.
Okay, so for example, instead of 7907, had it been a zillion, zillion is even, of course, but something in the zillions, then obviously 23 is very less, right? Or why
Right,
even go
yeah.
till why even go till zillion? I can give a simple example. 899. If you check till 23, you will conclude that it is prime, right? But it's not prime. It's 900 minus 1.
So you
So-
just always just check it with numbers that are prime, other numbers that are prime.
Yeah, that's what he's checking, right?
Yeah.
So he's checking 2, 3, 5, 7, all the way till prime numbers till 23 he's checking. And then there he says, okay, I'll stop here, right? I'm saying you should not stop here. I gave one quick example. 899, for example, is 900 minus 1. So a square minus b square is a plus b into a minus b. So he will not find that it's divisible by prime numbers till 23. Okay, Rohan?
So you look until the square root of the number, right?
Exactly. We have to look only till the square root of all prime numbers till the square root of the number, right? So obviously the other, why square root? Because the other pair factor, if at all it has two factors, I mean, if at all it has a pair of factors PQ, which multiply to give that number n, right? P will be smaller than square root of n, and Q would be bigger than square root of n. If it's equal to root n, then obviously it's a perfect square, in which case it is obviously prime, not prime, other than 1, of course, right? So it's enough to go till root n, approximately. So in this case, 7907, the closest perfect square, I mean, without too much of hand calculation, we can say 8100, right? So around till 90, approximately till 90, we need to check all the prime numbers. That is not a lot. There are only about 25 or so primes, less than 100, right? So not a lot. If you already covered to 23, you have quite a few actually. A lot of population of prime numbers initially, as you expect, and then they become sparse after that.
So 24 primes till 90.
24, huh? 24
Except
till,
for because 25 primes till 100, and I think 97 is the only prime after 90.
Okay. So we need to check 24 in this case. That's what you're saying, right? 24 checks. Yeah. Cool. Oh, by the way, talking of primes, you guys know what co-prime and twin prime are, right? So some people get confused.
Sir,
Yes.
I think the answer would be 23 because 89 would not count because square root of 7,907 is between 88 and 89.
Okay.
But it's not 89, so it wouldn't count, right?
Right. Yeah, it would not count. I just did very hand wavy. I just quickly did like 90. But yes, yeah, as you're saying, 89 square is probably, right, bigger than 7907. And therefore, we don't even need to check 89. So we can get rid of, so probably, what is that? 83 is the last one, I guess, right? You don't need to go beyond. Okay. All right. So talking of co-prime and twin prime. Okay. Do you know what these two terms are? Vivan, what is co-prime and what is twin prime?
So me?
Yeah, Vihan, yes.
So co-prime is basically those that have like the highest like the HCF is common or something like that, right? Oh,
HCF.
no. Co-prime is the one that they have no other common factors other than 1.
Correct. Give me an example of a pair of co-prime numbers.
5 and 7.
Okay. So any two prime numbers are obviously co-prime.
Yeah.
Can you give me two composite numbers which are co-prime?
No clue.
Come on, even in single digit
So
you can
maybe
find
12 and 49 or something.
12 and 49. Yeah, or why even
Oh,
go
yeah.
that far? 8 and 9, right?
This is
Is
So
also
all
good.
consecutive
yeah,
numbers
yeah.
are co-primes because there is no way you can,
Correct. All
except
consecutive
for
numbers
1
are
and 2.
co-prime.
Obviously, except for 1 and 2, but
Yeah, with
but
one
even then,
always
because
with
even
one
then,
it's
because
always
yeah,
thoda dicey, the definition. One is not prime. One by definition, one is neither prime nor
prime no
composite.
composite.
Yeah. Okay. But yes, you're right. All consecutive numbers are co-prime. But I specifically asked Vihan co-prime numbers which are both composite. So not all consecutive numbers will be composite, right? For example, 11 and 12, sure they are co-prime, but 11 is prime in this case, right? So to any two prime numbers, obviously they are co-prime. Any two consecutive numbers, obviously they are co-prime. But for two numbers to be co-prime, they don't need to be consecutive or they don't need to be prime, right? They can both be composite as the example I gave here, or I mean, and they can be far apart like 8 and 15 as well. Okay, that's co-prime. Okay, what about twin prime? What is twin prime,
So
Avinash?
twin prime. Oh, sorry.
Okay, fine. Avinash, yeah. What is twin prime, Avinash?
So I'm not sure.
Okay, Apurva, do you know twin prime? Yeah.
Yeah, so twin primes are primes that are like separated by one number. So like 11, 13, 21, sorry, not 11, 13, 17, 19,
Yeah, separated by two. Yeah,
5,
two or
7.
29, 31.
29, 31. Okay. Yeah, what is the largest twin prime less than 100? Can you guys think?
Will it be
41, 43?
71,
71,
73?
73.
71, 73. Yeah,
Oh,
41,
yeah.
43 team seems too small, right? In fact, even 71, 73 is very surprising. There are 30 more numbers left, but still the last twin prime is 71, 73.
So,
But
but there are
right,
not that many primes left. So.
yeah, that's what. The number of primes actually, it's actually very interesting, right? Then I forget the exact thing, but number of primes till n, if you take like for large n, okay, upon n. So in other words, let's say you want to look at the fraction of numbers which are prime till, let's say, till for example, for 100 the fraction was 1/4 because we saw 25 prime numbers till 100, right? For 1000 the fraction will become even smaller. You won't have 1/4, you'll have much less. Maybe, I don't know, someone has to look it up, but maybe 1/5. So the fraction will get smaller and smaller. So maybe there are 200 primes which are less than 1000. So the fraction of prime numbers until such a number. Sorry guys, I'm forgetting what that is. It's n factorial by n power n, something like that. I'll look it up and tell, or you guys can Google it also. Okay. Okay. Shit, it's there in my throat, but I'm forgetting now. It starts with S. Stirling's approximation. Stirling's approximation. We'll talk about that. Okay, look it up later. Stirling's approximation. So it's a very interesting result. The fraction itself will go to 0 because the number of, if you think as first Rohan was telling, right? The number of primes gets very less, very, very sparse. So if you do this fraction for a zillion, the number of primes till zillion divided by 1 zillion, it'll be a very tiny number, right? It won't be 1/10, maybe 100 or something, right? But if you normalize it by some other quantity, you'll get some 1 by e. You'll get 1 by e. I remember that 1 by e somehow. But you have to normalize it by n power 1 by n, something like that. Okay, sorry, I don't want to just give half-baked information, but look up Stirling's approximation. Okay, talks about the fraction of prime numbers till a particular number. Okay, so there is co-prime, twin prime, and right after 100, it's very interesting, right? Right after 100, 101 and 103 are prime, are twin prime, right? Are both prime, and therefore immediately after 100, after a gap, you get this, right? And in general, to assess in problems, whenever we have a certain number, right? For example, there's in 2021, right? And there's something based on 2021 in the year 2021, you might have had a problem like this, right? So always look for some perfect square near that to judge whether it's prime or not. In this case, it was interesting, right? It's just 2025 minus 4. And we know 2025 is a perfect square. How do we know that? Okay, any number ending in 5, uska square aapko pata hai. So let's say, I'll put some number M5, right? M5, right? M is a digit. 5 is a digit, right? M5 means not the product, but M followed by 5. So the square of this, you guys know the pattern of this, will end in 25. And then the stuff before this will be M into M plus 1. Do you know this? Ananya, did you know this one? No? Okay, so I'll take an example. For example, 75 square. I can quickly say I'll end in 25. I'll just have to put 56. That's 75 square. Similarly, 2025 was this 20 was product of two consecutive numbers. What are that? 4 and 5. The 4 is 45 square, right? So in general, if I have M5, uska square, it's M into M plus 1 followed by 25. Why is that? We can easily prove it. What does M5 mean? M5, if you put a bar on top of it, it means the number M5, okay? So this is 10M plus 5, okay? So now if you square 10M plus 5, what do I get? If I square this, I get 100M square plus 2 into 5 into 10, which is 100M, plus 5 square, which is 25. So I get 100 into M square plus M plus 25, which means if I have to write out this number, in the last 2 digits, it's 25, right? This is the units digit, this is the tens digit, this is the hundreds digit, this is the thousands, and so on. So in the hundreds place, what do I put? I put the product of M times M plus 1. Because after that, it's just 25. And that's what this is, 100 times M plus 1. So M times M plus 1 has a place value of 100 times that, right? Therefore, it's M times M plus 1 in the hundreds place, followed by in the tens and units, you have your 25, which is why it's easy to do a number ending in 5 ka square.
And what about the thousands place, sir?
Doesn't matter, right? It's M times M plus 1 could be a 3-digit. For example, had it been 115 square, right? The same logic holds. I'll end in 25. And in the hundreds place, I'll put the product of 11 into 12. 11 into 12 is 132. So it's 132 hundreds.
Okay.
Right? The number 132 itself has 3 digits, but it's 132 hundreds. So the 3 is the thousands place, the 1 is the 10,000s place, but doesn't matter. 132 hundreds, that's what matters. Okay. Okay, so where were we? So 2021 someone gives, right? Again, always look for perfect squares, aju baju mein, so which is easy to spot once you know the sum of patterns. And then now you know it's not prime. Why? Because this is 45 a square minus b square to your rescue. It's 43 into 47. And 43 and 47 are both primes. So if some question was something related to 2021, right? And something related to the prime factorization, you can get yourself ahead by a few paces if you figure this out quickly, right? And then you'll know it's 43 times 47. And if you check for prime numbers till what Kunz did till 23, you will wrongly infer it as prime, right? But now you know it's not prime. And then that will lead you to something else. Maybe the number of factors that this guy has. Very easy now. It has only 4 factors, right? 1 plus. So this is power 1, this is power 1. Both of them are prime. Okay, so always look for, which is why I keep harping. You should know all perfect squares at least till 1000, and then all of these basic patterns ending in 5. Recognizing some 899 that I gave you was 900 minus 1. So if you look for a perfect square around it, then you will see it's 30 square minus 1 square. Therefore, it's 29 into 31. A plus b times a minus b. Okay. So 7, 9. Okay, now the next one is the puzzle on the doors. This is a fairly common puzzle. Some of you might have heard of this already. Has anyone, actually, should I ask, has anyone heard or not heard? Okay, fine, I'll ask, has anyone heard of this puzzle before?
I've heard of it before, sir.
Okay, all right, so I'll skip you then. Someone else who has not seen this before, can you answer, like, what did you get on this one?
So,
Yes, go ahead, Apurva.
yeah, so I got 31 doors.
31 doors. Okay, what are those doors?
So all perfect squares.
Okay, and why so?
Because perfect squares are the only numbers that have even number of factors.
Odd number of
And-
factors.
Sorry, odd number of factors. And because of the odd number of factors, they start as closed, and including one, since they have an odd number of factors, they will end as open doors. Whereas all other numbers have pairs of factors. So like they'll multiply with something else.
Perfect. Yes. Right. So all numbers will have even number of factors other than perfect squares, because when you write out factors itself, you are writing them in pairs like this, right? Like this, right? But only with perfect squares, we have odd, because we get something like 21. And let's say we're looking at 441, sorry, right? We'll write 1 into 441, 3 into blah, 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 and so on. And then it will be 21 into 21. The number 21 is repeating, therefore it has odd number of factors, right? And of course, all prime numbers have even factors, so they'll all be in the closed state. But not all numbers which have even factors are prime, right? In fact, the vast majority will have even number of factors. Only the prime numbers, only the perfect squares will have odd number of factors, as Apurva was saying. Another way to think about the same thing is if you do the prime factorization, right? 2 power a times 3 power b times 5 power c and so on, right? The number of factors, I'll call it f of n, right? The number of factors f of n is a plus 1 into b plus 1 into c plus 1 and so on, right? That's what we do. We have been learning this for quite some time, right? D power plus 1. Okay. Now, if you look at it, right, this is product of several numbers. Even if one of these numbers is even, even if one of these numbers is, even if one of these numbers is even, then the product will be even, correct? Even if one of these numbers, a plus 1 or b plus 1 or c plus 1 or d plus 1, for the product to be even, all it takes is just one even number, which means, right, if either a, b, c, or d, any one of them is odd, then we'll have even number of factors, right? I'll repeat again. A plus 1 or b plus 1 or c plus 1 or d plus 1, any one of them is even, that's it. The product is even, therefore it has even number of factors, which effectively translates to if either a or b or c or d is odd, then it has even number of factors. The only possibility when a, b, c, d will be odd, right? Sorry, was I saying it reverse? Yeah, correct, right? Yeah, so if it's a perfect square, then a, b, c, d, all of them will be even, right? I don't know. Did I mess up saying anything? I'm sorry, guys, if I uttered something rubbish. But point is, for a perfect square, A, B, C, D, all of them will be even. Which means when you add one, you'll get a product of odd numbers. Only then the product will be odd. Again, back to what he was saying, right? Only then you'll have odd number of factors. For something to have odd number of factors, A, B, C, D, all of them have to be even, which means effectively we are talking about a perfect square, because it's a number like 2 power 14 times 3 power 6 times 5 power 8 times 7 power 0, right? 7 power 0 does not even mean anything. 7 power 2, right? Only then I can write it as 2 power 7 times 3 power 3 times 5 power 4 times 7 power 1, the whole square. So it becomes a perfect square. Okay, again, I'm just repeating whatever I'm saying multiple times. Okay, cool, nice. All of you understood, right? The solution that
So
Apurva
can you
gave?
just explain how you got to this odd number of factors itself? What was the question asking? I couldn't understand.
Oh, sorry. Okay, the question was there are 100 doors or 1,000 doors, whatever, right? And an operation happens on every night, first night, second night, third night, fourth night, all the way till 1,000th night. On a random night, let's say the 5th night, what happens is the doors which are numbered 5, 10, 15, 20, all the way till 1,000, all the multiples of 5 are flipped. Flipped means their position is changed. If it's closed, it's opened. If it's opened, it's closed, like this, right? And the question is, at the end of these 1,000 nights, what state will the doors be in? Which will be open, which will be closed? So for that, what Apurva was telling was, if I take any one door, let's say I take the 240th door, 240th door, right? So 240th door will get touched by on the nights of 1, 2, 3, 4, 5, 6, 8, 10, and so on. All the factors of 240. How many factors does 240 have? if you list out like this in pairs, right, it has even number of factors. So
Yeah.
whatever happens gets undone. Whatever happens gets undone. So at
Oh,
the
okay, so
final
it's
stage,
of an odd number factor, so it has to be perfect square.
exactly, right? So ultimately, the story boiled down to only this: how many factors, the number of factors, parity. You don't even care about number of factors. You only want to know if it's odd or even. That's it. Because whatever gets done gets undone if there's even number of factors. Okay, makes sense. Okay, that was question 7. Okay, question 8. How many factors of these are perfect squares? Okay, Kunal, what did you get on this one?
I didn't get till here.
What do you mean you didn't get till here? I mean, what does that statement mean?
I solved till the 6th sum.
Oh, okay, I see. Okay, anyone? Ananya, what did you get on this one?
I got 32.
Okay, just 1 second, guys. Someone is messaging me. Okay, 32. Okay. Anyone same answer, 32? Vihan?
So even I got 32.
Apurva,
So
you also
even I
32?
I got
Okay.
this one.
All right. Okay. So let's ask Sana, what about you? Were you able to do this one, Sana?
So I don't think I was able to do it.
Okay. All right. Who was I asking this? I forgot. Who called out 32? I forgot now.
Oh, sorry, 32.
Ananya. Okay. Yeah, Ananya, can you tell me how 32, please?
So I listed out all the prime factors.
Yeah.
Um,
So with the prime factorization of this was what? So this is 3 square and this is 10 cubed and 10 cubed, right? So it's
Yes.
3 square and 2 power 6 and 5 power 6, I guess, right? Okay. Then
so then I listed out all the even powers, like 3 to the power 0, 3 to the power 2.
Yeah,
2 to
perfect.
the
Yeah, correct. So to take an even, to take a perfect square, how shall I say this? If you need a perfect square to be a factor of it, I can either pick 0 2s or 2 2s or 4 2s or 6 2s. I have 4 choices here. From the 3 basket, I can pick either 0 3s or 2 3s. From the 5 basket, I can pick either 0 5s or 2 5s or 4 5s or 6 5s. Therefore, I have 4 possibilities of picking, 2 possibilities of picking, 4 possibilities of picking. Therefore, 32 indeed. Okay, makes sense to everyone? Anyone who did not get 32, does it make sense now? Okay, let me ask an extension to this question, right? I will ask how many of these factors are, okay, I'll insert either perfect cubes or perfect squares. Okay, so now can we do the revised question? Either perfect cubes or perfect squares.
So I got 37.
37 from Ananya. Okay, all right. Anyone else agree or disagree with her?
So I'm getting 41.
41. Okay.
Yeah, but there's double counting in that, so I'm not sure how do I like eliminate the double counting.
Yeah.
Oh yeah, wait, so I forgot about the double counting. Once.
So I'm getting 39.
39. Okay.
So I'm getting 37.
Okay. 37. So a couple of 37s.
Yeah, so I'm getting 37.
Okay,
instead of
all right.
41, yeah.
Yeah. So all of you are
Yeah.
close. And yes, 41 is without the double counting, as Avinash was saying. But
Yeah.
are people doing the double counting correctly? So 39, 37. Okay, let's see, right? So perfect squares are these. For perfect cubes, I should, same logic. I can pick either 0, 3, or 6 number of twos. Only choice is 0, 3s, and 0, 3, or 6 number of 5s. So 3 into 1 into 3. So I have 9. And therefore, the first initial attempt would be 41. And now we realize there is double counting. Double counting happens when it's both a perfect square and perfect cube. Therefore, if it's either 0 or 6 here, or just 0 here, and 0 or 6 here. So it's 2 into 1 into 2. Right? So yes, there are 4 of them. Therefore, when you subtract, these are the powers of, which are 6th powers, right? Which are both counted in squares and cubes, which is, so A union B essentially is what we're doing, right? Cubes or squares, which is the number of elements in A plus number of elements in B minus the intersection. So it's 41 minus 4. 32 plus 9 plus, so this is 32, this is 9, this is 4. So which is 37 indeed. Does it make sense? Okay, well done, Ananya and others who got 37. Did you find a mistake, Apurva, with for 39?
Yeah, so I didn't eliminate the double counting correctly. I missed 2 cases.
Okay, all right. Now let me ask one other way of counting, and then it's wrong, but I want you guys to say what is wrong. So the question is either perfect squares or perfect cubes. So what if I do something like either perfect squares or perfect cubes? So as far as 2 ka power is concerned, it can be 2 power 0, 2, 3, 4, or 6. 3 ka power can be 0 or 2. 5 ka power can be same thing, 0, 2, 3, 4, or 6. So if I do this, I get 5 choices here, 2 choices here, 5 choices here. So I get 50. What is wrong in this approach? Perfect squares or perfect cubes?
So it'll say that 2 raised to 3 into 5 raised into 3 raised to 2 into 5 raised to 0. That's not a perfect cube or a perfect square.
So we've done this exact discussion.
Oh, is it? Did we do
We
this?
did this last
Yeah.
time.
Oh, okay, okay. All right, good. Okay, yeah, exactly what, and I'm glad that you guys even recall the discussion. I don't, but nice, yeah. So basically he's saying I can have a mix, which is neither here nor there, right? If I have something like this, so this number is cube, this number is a square, this number is a square. When you multiply, it's neither a square nor a cube. Okay, cool, well done. Okay, question 9. Find the least number of which leaves a remainder. Okay. Anyone, Rohan, did you get this one?
So which part do I answer?
Okay. First answer the first part.
I got 3023.
3023. 3023. Okay. Anyone get the same answer? Same.
I got 503.
503.
So
Okay.
even I got 503.
Okay. All right. Rohan, can you explain your 3023?
So I started solving it normally, but then I thought that, oh, they're all -1, right? So if I got to a number that was that was 5 times, that was 6 times, 7 times, 8 times 9, and I -1, it would fit all the criteria. So I stopped doing what I was doing, which was, listing all the numbers 5, 11, 17, like that. And then I saw that pattern, and then I found 3023.
Yeah. The only one small mistake you did was you don't need to multiply. You only need to find the LCM to find the least. So it's LCM
yeah.
-1, not
Oh,
the
yeah,
product
yeah,
-1, but the LCM
yeah.
-1. Okay. And probably based on the other 2 answers, the LCM is 504 probably, right? So 6, 7, 8. Okay. Just so that others are plugged in. Kunsh, did you follow or did you do this?
Yes, I
Understand?
did this. I got 503.
503 as well. Okay. So Avinash, you're okay on this one? How you get 503?
So I didn't do this.
Okay. But do you understand now from the discussion how it's LCM -1?
Can you just explain it again?
Okay. Okay. All right. So forget about leaving a reminder. Okay. What number divides exactly with 6, 7, 8, and 9? Exactly divides 6, 7, 8, 9. The smallest number. It's the LCM. So LCM of 6, 7, 8, 9. Let's say that number is n, right? n when divided by 6, 7, 8 or 9 will leave a remainder of 0. That you agree, Avinash? Right?
Yes. Oh, and
Yeah.
then n plus 1 will be.
Yeah, n will leave a remainder of 0, 0,
Yeah.
0, 0. N plus 1 will leave a remainder of 1, 1, 1, 1. If I do n minus 1
will
instead,
be 5, 6, 7, 8.
exactly, because it's just one short of reaching exact multiple, right? Therefore, n minus 1 is exactly what you want. So all you want is the LCM. So I'm guessing the LCM was correctly calculated, was 504. Therefore, 504 minus 1 is 503. Which will be the next number after 503, Apurva?
So the next number after 503, I guess, will just be 504 into 2 minus 1.
Good.
You
right?
can't do 503 into 2 because then you won't get the number. You need the LCM minus 1.
Exactly. That's exactly what the mistake was trying to allude to. Good that you did not do. So it's 504 minus 1 is the first one. The next one is 504 into 2 minus 1. And not 503 times 2. Right? It's obviously it must be a multiple and then subtract 1 from that. So the next one be 3 times 504 minus 1. And therefore, for the second part, how many will there be, Apurva, till 10,000?
So that'll be 19.
Yeah, approximately 20, right? So obviously with this, if it's
Yeah, with
20
the
times 500, it will become 10,000. Therefore, that will exceed, when you do multiply by 504, it will exceed, right? Therefore, this will exceed. Therefore, 19 is the number of numbers which are
So-
less than 10,000. Yeah, well
So
done.
also, like, I have to leave now because I have to go somewhere.
Oh,
My
yeah,
mother
yeah,
had
yeah,
messaged
yeah.
me.
Your mom had posted a message. Yeah. Okay. Watch the recording for the rest of the
Yes.
class.
Thank
Okay, cool. Okay, so that's done. That was the last question. Is in this? Okay. All right. So I just wanted to next move on to just a review of permutation combination. Right. Let me just go through the topics for AMC10. So we did AP, GP, rate, speed, telescopic cancellation, quadratics. We did squares, cubes, safe LCM, divisibility rules. Okay. Pythagorean triplets. Tutorials. Okay. So one other thing in terms of reminders, you should know the formats. There are a few reminder theorems. The formats little theorem is important, right? To calculate reminders. So this says, if I have a number a power p minus 1 is 1 mod p. Okay, so first of all, what is modulus? So okay, so before we do this one, right? So we have, so suppose I have number like 27. So 27 is 3 mod 6, which means what? When I divide by 6, it leaves a remainder of 3. So 27 is 2 mod 5. When I divide by 5, it leaves a remainder of 2. 27 is 0 mod 3. When I divide by 3, it leaves a remainder of 0.
So
When I
what is
divide,
the 3 dashes mean?
it's equivalent to, right? So it's not equal to, but people put equivalent to, but it doesn't matter, right? You can put 2 equals also, that's fine.
Okay.
Effectively, same thing, right? We're talking about 27 is equivalent to 3, right? This is to be read as this way. 27 is equivalent to 3 when you're dividing by 6 in terms of the remainder, right? Both leave a remainder of 2. That's what it means. So 27 is equivalent to 2 when you divide by 5. Both leave a remainder of 2, right? Meaning 2 when divided by 5 leaves a remainder of 2. So, and 27 is equivalent to 0 when you divide by 3. 27 is equivalent to 0 when you divide by 9. So the way you write it is like this. Okay. So, so you understand the notation now, right?
Yes, sir.
I'm frozen. Hello. Hello. Am I frozen? Am I okay? I got disconnected for
Yes,
a bit. I
sir,
thought.
fine now.
Okay. My connection is showing as unstable. The last I heard was Avinash was saying yes, sir, when I did not even ask a question. So I don't know what that yes, sir was. All okay? Okay. So if P is a prime number and if A is a multiple of P, if A is a multiple of P, then A power, okay. So A is not a multiple of P. I'll just say A is not a multiple of, not a multiple of P. Okay, why is this not multiple of P, right? Now, this thing is talking about a power P minus 1 leaves a remainder of 1 when divided by P. That's what the statement is. Of course, if A is a multiple of P, then a power P minus 1 will obviously be a multiple of P. Well, A itself is a multiple of P. If you raise it to some power, obviously that will also be a multiple of P. It'll leave a remainder of 0 only, which is why he says a power P minus 1, if A is not a multiple of P, leaves a remainder of 1. Okay, let's take an example. I think that's the best way to understand, right? So I'll choose P as the number 5, okay, or even 7. Okay, P is number 7. Okay, and A is the number. A need not be prime. A could be prime, doesn't matter. A should not be a multiple of P. That's all, right? So if I take A is 12, okay, so 12 power 6, right? 12 power 6, when you divide by 7, leaves a remainder of 1. Okay, can we just pull out your calculator and just check this? 12 power 6, when you divide by 7, can you check if it leaves a remainder of 1? Can one of you do this? So 12 power 3, we know it's Ramanujam number related, right? 12 cubed is 1728. 1729 is Ramanujam number. So this is 1728 whole square. So we'll need your calculator. Can someone check this? Just 1 second, 1 second.
So it works.
Okay, did someone check 12 power 6 divided by 7 leaves the remainder of 1?
Yes, sir.
Yeah, yes, sir.
It works out, right? Okay, now this is very useful in finding reminders. In general, with finding reminders is useful. Okay. Okay, so in general, how do you find reminders? So for example, if I want to know, I think we've done problems like this, right? So 3 power 100, okay? When you divide by, let's say 19, okay? What's the remainder, okay? So can you guys take some time to work it out? 3 power 100 divided by 19, what is the remainder?
So we find the remainder, right?
Yeah, find the remainder, yeah.
So will it not just be wait. Won't it be 3?
Could be 3. I'm not saying it's not, right? It could be. I haven't worked it out myself. I thought we'll do it together. Yeah. You don't even necessarily need this Little's theorem. Obviously, it'll be very useful if you know it, but you can do it even without that, like little intuitively. Let's do it with and without.
So I got 12.
You got 12. Okay. Any number less than 19 is valid. 0 to 18, your number should be. So he got 3, you got 12. Let's discuss, all right? So let's use the remainder theorem. So I'll pick A as 3, P is 19. So 19 is prime and 3 is not a multiple of 19. That's all we care for. 3 could be prime, 3 need not be prime, doesn't matter. Smaller, bigger. It's not a multiple of P. That's all matters, right? So 3 power 18 is 1 mod 19, right? Which means 3 power, which means to say 3 power 18 is a number which is 19 times some integer plus 1. That's what it means, right? It's some multiple of 19 plus 1. So now I want 3 power 100. So I can say 3 power 18 whole power 5 is 3 power 90, right? So 3 power 90 is 3 power 18 whole power 5, right? Which is nothing but 19k plus 1 whole power 5. 19k plus 1 whole power 5. Now, when I do 19k plus 1 whole power 5, you'll have the binomial expansion of that, right? So all of the terms will have 19 power 5, 19 power 4, all of that. All of those terms will have 19, 19, 19, except the last one, which will be 1 power 5, which is 1. So this whole collection is some other multiple of 19. I don't care, it is 19 times some other big number m. So the advantage of having a remainder of 1 is that, right? If you keep multiplying by any power after that, it'll still be 1, 1, 1, 1, right? Because 1 power anything is 1, right? And the rest is anyway a collection of multiples of 19. Is this clear so far? So 3 power, we have already got till 3 power 19, 3 power 90. So effectively, we want 3 power 10 times some number which is 19m plus 1, right? Uska remainder, right? Now, again, the advantage of 1 is, let's say 3 power 10 is some 19n plus some r that we are seeking, right? The remainder r that we are seeking. When you do 19m plus this, when we do this, effectively the remainder will be r only, right? This implies the remainder is r. Why? Because when you do 19 times 19, that's a multiple of 19. This is also a multiple of 19. This is also a multiple of 19. R times 1. Right? So all that matters is the problem reduces to what is 3 power 10 per remainder when divided by 19. Is this clear? Because when you multiply by 19m plus 1, the remainder will be r times 1, which is just r. Right? So 3 power 10 is a fairly small number. We can get to it very quickly. But easiest way is just to find some number which is, okay, fine. We can do 3 power 5 whole power 2, right? And from here on, there are multiple ways, right? You can choose whatever is convenient. 3 power 5 is how much? 243, right? And we can quickly divide by 19 and see what the remainder is. 19 ones are 19, 53, 19, how much? 3s are, sorry, 19 2s are 38. Remainder is 15. Okay, so this is some 19 times something, 12, but I don't care what the 12 is. It's some 19 times some number L plus 15 is what I care, right? When I do this square, effectively it's equivalent to 15 square because the 19L will not matter, right? Because only care about reminders, I can keep dropping multiples of 19. So effectively it's 225 divided by 19, it boils down to. And that is just a simple process, right? 35, 19 ones are 19, the remainder is 16. Does it make sense? Okay. Rohan, what was your mistake to find?
Sir, I had done for Fermat's rule theorem, I had done 3 raised to 17 by accident. But while you were explaining, I redid the sum and I got 16. Yeah.
Okay. Okay. You subtracted like one more, right? You wanted to subtract and then you thought you didn't subtract and then subtracted was
probably.
Yeah. Okay, happens. And was Avinash, how did you get? I think you said 3, right? As the remainder. How did you get
I misheard the theorem. That's why.
Okay. All right. And then you don't even we don't even need this theorem. We can still do it even without it. Like just by how the last few steps we did it without the theorem, right? We can still do the same thing, right? So 3 power 100. Suppose I didn't know this theorem at all. I can still do something. I'll keep searching in powers of 3, right? Which are close to a multiple of 19. So 27 is still somewhat apart from multiple of 19. 81 is fairly close, right? 81 is 76 plus 5, right? So I'll go with that. And it also happens to be a factor of 3 power 4 whole power 25. Right? I'm not even using Fermat's theorem now. Right? I'm just using 3 power 4. Now this is 19a plus 5, 76 plus 5. So it's some. So effectively, my problem reduces to 5 power 25. From 3 power 100, I've shifted to another prime number. It's 5 power 25. Now I'll start my analysis with powers of 5.
So,
Yes.
this thing, you got 3 raised to 100, 3 raised to 4 raised to 25.
Yeah.
Why do you get the 19a plus 25? That main step is.
No, because I want to divide by 19 and then see the remainder, right? So I explore powers of 3 and see where I'm fairly close to multiple of 19.
Yeah, got it.
81 was fairly close. So 76 plus 5.
Okay.
Okay, now I shift gears to the 5 wala. So I'll keep searching 5 Azubajube, 125, 25 is fairly close. But let's also try a little bit more, right? Which is why you need to know like multiplication tables fairly well, right? 125, fine. Okay, I'll take 25. The 25 is right? Or let's go a little bit more, right? 625, 3125. How sorry?
No, I was saying 25 is just plus 6.
Plus 6, right? But at least it reduces by half. So fine, I'll just explain the process. Maybe 25 is not the closest. That's fine. And also it's not a factor of 25. So it's fine. So we'll still go with 25. So it's 5 power 2 whole power 12 plus another additional 5. So 5 power 2 is 25. So 25 is nothing but some 19b plus 6. Okay, so it's effectively 6 power 12 times 5 is what I'm looking at. So 6 ka series, I can start a little bit. 6, 36, 216. Okay. Okay, so 216 is fairly close, right? So this is when you do divide by 19. 19 ones are 19, 26. 19 ones are 19 plus 7, right? So 11 times 19, right, is 209 plus 7. So this can be replaced as 6 power 3 whole power 4, and 6 power 3 is some 19 times some number c plus 7. So effectively, we are talking about 7 power 4 times 5. Now it's fairly close, right? So 7, I can write this as 7 square whole square, right, times 5, right? 7 square is 49. 49 is 38 plus 11. So it's 11 square times 5. So it's effectively 121 times 5. And here I can just manually finish it off from here. So 605. 605, right? 605. Okay, let's do it and see whether we get the same answer. Huh? So 19 threes are 57. 35. Yeah, 19 ones are 19. Remainder is the same 16. Right? But we have to go like several hops. Right? The Fermat's theorem helped us get a one big hop initially itself. That's the only difference. Okay, all right. There are a few other remainder theorems also, like Euler's theorem and Wilson's theorem, something. But this is the main one. I don't want to over confuse you. For AMC10, this is good enough, right? So not to confuse. I mean, they're all very useful only and not very complicated. If you know them, it's good tricks to have for the future. Okay, all right. Let's do some basic revision of permutation combination. Since some of you may be new to the topic, some of you might need a refresher, right? So there are two things. One is choosing and one is arranging, right? So choosing is, so let's say there are 10 students. I have to select 3. So that's 10 choose 3. Avinash, have you been through permutation combination?
Yes, sir.
In the earlier sessions that we did, or with me here, or?
No, I don't think so, sir.
Oh, okay.
We've done,
Yeah.
I think we did it once or twice, like in question papers, but we never did it properly.
Okay, all right. So I'm only going to do a very quick refresher. That's it, right? So when I have number like 10 choose 3, I have to select 3 people from 10, right? So these 10 people are sitting here, right? So I can call any one of the 10 first. I can call any one of the 9 and any one of the 8. But then I figure that the ordering does not matter. Let's say I call B and then let's say A, B, C, D, E, F, G, H are the people. Then I call G and then I call A. Whether I call B, G, A or A, G, B or A, B, G, all of them are same. So I'm double counting. Double as in double within quotes. I'm multiple counting. I'm multiple counting in the number of ways in which you can arrange A, B, and G. right? All of them are equivalent, right? There are 3 factorial ways of arranging A, B, and G. Therefore, 10 choose 3 is 10 into 9 into 8 by 3 into 2. There is no arranging at all, right? That's just choosing, right? And just to give a more simplified notation, so rather than write out like this, you can artificially multiply and divide by 7 factorial. That way, the numerator gets completed to be 10 factorial. And the denominator is 3 factorial times 7 factorial, right? This is just a trick to just write it more concisely for a more general n choose r. So n choose r just becomes n factorial upon r factorial times n minus r factorial. Okay, so notice that the denominator is symmetric. So when I choose n minus r, it will become n factorial by n minus r factorial times n minus r, which will become r. So these two are equivalent, right? It's just the ordering of r factorial and n minus r factorial is reversed in the denominator. So both are equivalent. So what is the meaning of this? So if I have to select 96 people in a class of 100, right? It's effectively choosing 4 people in the same class. And that's what practically someone would do, right? You're not going to select 96 people. Let's say 96 people are allowed to represent the school. The school has 100 students and some competition. 96 spots are there, right? You're not going to be selecting which are the best 96 from your class of 100. You'll select the worst 4, and let's say that you guys are eliminated. The other 96 are good to go. So the act of selecting 4 automatically is equivalent to act of selecting 96, because we only care how many ways to select. What we do with that selection is a different thing. If you're able to partition 4, the other 96 are already partitioned, right? So it's always easy to think in terms of smaller numbers. So 100 choose 96 is same as 100 choose 4. Likewise, the extremes are important, right? 100 choose 100 is same as 100 choose 0, right? So how many ways can you select 100 out of 100? Only one way. How many ways can you select 0 out of 100? Again, only one way. The act of not choosing anyone is one way. Okay. Similarly, so this is n. So this is n choose 0 will be always be 1. N choose 0 same as n choose n, which is 1. And similarly, n choose n minus 1 will be same as n choose 1. These are n choose, which is just n. So n choose n minus 1 and n choose n. And n choose n minus 1 and n choose 1 will both be just 1. It will be just n. Oh my God, so many slips in what I'm telling, right? So this is just n. And that again, you don't need too much permutation combination for this. 100 people, how many ways can I select one person? Any kindergarten will tell it's only 100 ways. How many ways to select 99 people? Same, I don't have to select 99, I just have to eliminate one. So 99 ways for that as well. Okay, so these are the common ones. Of course, n choose 2 is n into n minus 1 by 2. N choose 3 would be n into n minus 1 into n minus 2 by 3 factorial and so on, right? Okay, that's choosing. Now, arranging is what? Arranging is, okay, we can keep the arranging game separately. So let's say there are r people. Okay, r people, you have to arrange in a straight line. There's r factorial ways, right? Because the r people are already chosen, right? In fact, we're not even thinking about some choosing. You're given r people. You just have to lay them out on a straight line. So I can call any one of the r to occupy the first spot, any one of the remaining to the second spot, and so on, all the way till the last guy does not have a choice. He has to sit in that available spot. So r factorial ways of arranging. Okay. Now, choosing and arranging could be combined. So for example, someone could say of 10 people in a class, how many ways can the gold, silver, and bronze awards be given, right? So first have to select which are the top 3, right? And after having chosen the best 3, you can give them in any order, 3 factorial ways. So the combination of n choose r times r factorial gives the arranging as well, right? Which is called NPR, but I try to avoid NPR as much as possible. So it's a little confusing. No, not confusing. It's best to keep the choosing and the arranging separate. And as and when needed, you can just multiply it out. Right now, it's not very complicated to multiply, right? So this becomes this, and this becomes times r factorial. The r factorial therefore gets cancelled. So leaving just n factorial by n minus r factorial. Okay, that's arranging, right? Choosing and arranging. Okay, and when it comes to arranging in a circle, that's important. Arranging in a circle is, for example, let's say I have 6 people have to sit in a circle. 6 people sitting on a straight line, it's 6 factorial ways they can sit. That's very obvious. If 6 people have to sit in a circle, there are only 5 factorial ways of arranging them. Okay, so by that, what do I mean? You have to be very careful about what you mean by sitting in a circle. Sitting in a circle on a relative basis, right? So let's say these are 1, 2, 3, 4, 5, 6 spots, right? On a relative basis, when you're sitting, there are only 5 factorial ways. Of course, if there is let's say this is the restaurant and this is the kitchen, right? And people who are sitting close to the kitchen will get delivered first, right? Then this seat becomes special seat. In that case, it's effectively like a straight line only, right? It's not like just because it's a circle, it's 5 factorial ways. So whenever a particular seat has a priority, a circle is nothing but a straight line. It's only when you're in space, right? And nothing else is there around you. Everything is relative. It's only among the 6 friends, wherever they're sitting left and right. That's all matters. Then it's only 5 factorial ways. Why only 5 factorial ways? There are 6 friends here, A, B, C, D, E, F, right? So let's say one guy first comes and sits somewhere, doesn't matter. D comes and lands here, doesn't matter, wherever that spot is. Okay. After that, relative to him, everyone can start sitting. So who's sitting to the, is it left or right? I'll just say right. Who's sitting to the right of T? That can be any one of the remaining 5 people. And from there on, 3, 2, 1. So which is why one gets knocked off, right? Because someone comes an entry and sits somewhere.
So, but say that you're having a circle, but all of them are free. And then there are 6 people to fill the 6 slots. How many options will there be? Will it be 5 factorial or 6 factorial?
Okay, the question has to be very clear. If the seats are all identical and we are only talking about relative positioning between them, it's 5 factorial. But if the seats have some color, let's say the seats are red color, white color, black color, whatever, right? Then it's effectively like a straight line because you are able to distinguish one seat from the other. It's not merely relative. It's effectively like a straight line only. Right? Again, the other example I gave was, so the door, there's a kitchen door, and which means there is some speciality associated with each seat or even one seat, right? So okay, this is best works if you think like you're floating in space and it's like constantly rotating table, right? So that symmetry is there. So doesn't seat has any speciality over the other. In such a case only, it's n minus 1 factorial. Again, the question should be very crisp. When it states this, it should not be ambiguous, but there's a lot of ambiguity generally in questions related to circles. But generally, AMC does a pretty good job in the questions. The Asian Olympiads are definitely confusing. They always make some slips, or the question is not very crisp and clear. It could be read both ways, all that. But AMCs they make sure the question is very clear. Okay. All right. I'm going to end the call a little earlier today. Let's stop here. I'll give questions on permutation, combination, probability. Pretty much we have covered all the basics that's needed. From next class onwards, we can start doing topical based questions in detail. Okay. All right. I'll see you next week then. Okay. Whoever is not caught up on homework, the first few, please
Thank you,
work
sir.
on them.
Bye.
Okay. Thank you. Bye.